In October 2012, Norwegian Cruise Line, NCL, announced the order of its first Breakaway Plus class ship from the renowned German shipbuilder Meyer Werft, with an option for a second vessel. These ships represented an evolution of NCL's earlier Breakaway class, featuring a significant size increase of approximately 17,000 gross tons, GT, bringing the total to 163,000 GT. This expansion allowed for enhanced passenger capacity and the inclusion of new amenities and attractions. By July 2013, NCL confirmed the order for the second Breakaway Plus class ship at a reported cost approximately €700 million. With the initial ship already on order, the total contract value for the two vessels reached an estimated €1.4 billion, marking a major investment in the cruise line's next generation fleet. In October 2013, NCL revealed the second Breakaway Plus class ship would be named Norwegian Bliss, selected through a public naming contest conducted in September. However, in October 2015, the cruise line pivoted, announcing that this second ship would be deployed to the Chinese market. Consequently, it would no longer carry the name Norwegian Bliss. By February 2016, NCL officially announced the new name, Norwegian Joy. The ship was specially tailored to cater to the Chinese cruise market, incorporating design elements, amenities, and services that reflected local preferences and cultural nuances. Construction of Norwegian Joy commenced in September 2015 with the traditional steel cutting ceremony at Meyer Werft shipyard in Papenburg, Germany. The keel laying and coin ceremony took place in April 2016, marking a significant construction milestone. A ceremonial coin was embedded beneath the first of the 80 prefabricated hull blocks, a maritime tradition symbolizing good fortune. The ship's first major hull segment, measuring 120 meters, 390 feet, was floated out in June 2016. High-tech afloat, ships from Meyer Werft. The most important element for building ships is steel. Liquid steel is shaped into large blocks in steelworks, that's Meyer Werft. Shipbuilding steel is transformed into highly sophisticated cruise ships. First, the designers' blueprints and the strength calculations for the ship's construction are translated into technical drawings. Thus, shipbuilding begins. The steel construction process starts in fast motion. Individual steel plates measuring 3 by 10 meters are joined to make panels measuring up to 35 by 25 meters. These are reinforced with profile beams and girders before the walls are mounted. Several such flat sections come together to make blocks. One cruise ship consists of 50 to 80 of these blocks. Meyer Werft has developed an innovative procedure, laser hybrid welding. This entails using a laser in combination with solid wire. Laser hybrid welding is much faster while producing better technical results when it comes to the weld seams. Let's take a closer look at the steel construction process. After the steel plates have been cleaned and treated with a corrosion inhibitor, they arrive at the shipyard. In the laser center, the steel plates are marked and cut to size using a plasma torch. The building components either go straight to assembly or are stored temporarily in the high-rise rack. All the plates are laser welded to create larger panels. On the panel production line, production is fully automated. To ensure precise weld seams, the edges are finished using a milling machine. During laser welding, precision is monitored using optical methods. The plates are aligned before laser hybrid welding begins via horizontal and vertical cameras integrated into the welding head. Profiles are mounted onto previously marked areas of the panels. After they are clamped laterally, the profile is tensioned using a clamp shoe and a pressure roller. The back holders overbend the sheet metal during the welding process. A vertical camera monitors the positioning line to align the profiles. The walls of each section are produced according to the same principle. The so-called jig frame consists of a large number of metal blocks, each of which can be hydraulically adjusted in height. In this way, building components featuring ramps or varying heights can be manufactured without any problems. In semi-automatic construction, the building components are produced as required. In the section pre-fitting phase, pipes, cable systems, and air conditioning shafts are pre-installed. Blocks are made up of approximately 10 sections, and about 70 blocks go into the construction of a large luxury liner. Machine construction is done in parallel with steel construction. After that, interior outfitting is completed. Now, 30,000 tons of steel have been transformed into a high-tech product. Unfortunately, 2 construction-related fires affected the build. In September 2016, a fire caused by welding work resulted in damage estimated at 50,000 euro. A second fire in October 2016, also linked to welding, broke out on a balcony and damaged several cabins. Despite these setbacks, Meyer Werft announced in November 2016 that the project remained on schedule. In March 2017, Norwegian Joy was floated out of the dry dock. Later that month, she began her 14-hour conveyance along the Ems River from Papenburg to Eemshaven, Netherlands, a process that required extensive coordination to navigate narrow waterways and bridges. Sea trials in the North Sea followed throughout late March, where performance, safety, and maneuverability were thoroughly tested. Engineering and propulsion. Norwegian Joy is equipped with a robust propulsion and power system. 5 main MAN B&W engines, 2 14 Vol 4860 CR engines, 22,520 horsepower each, 3 x 12 Vol 48/60 CR engines, 19,300 horsepower each. Total engine output, 102,900 horsepower. Propulsion, 2 x ABB Azipod XO azimuth thrusters, combined power output, 40-minute service speed, 22.5 knots, top trial speed exceeded 25.0 knots. Sustainability technology, fitted with an air lubrication system, which releases a stream of microscopic air bubbles along the hull. This reduces drag and enhances fuel efficiency, reflecting growing environmental priorities in cruise ship design. Comprehensive overview of ship maintenance, principles, practices, and optimization. Maintenance is the backbone of operational reliability for any mechanical system. Whether it's a compact machine or a large-scale structure like a ship, structured and efficient maintenance plays a pivotal role in ensuring safety, prolonging asset life, and maintaining operational effectiveness. In the marine industry, where mechanical complexity meets challenging environments, maintenance assumes critical importance. The reliability, safety, and economic efficiency of marine vessels directly depend on a well-planned and executed maintenance strategy. Join machinery and technology as we explore the fundamentals and advanced concepts behind ship maintenance. The importance of maintenance planning in the maritime sector. Maintenance planning is a foundational pillar in asset management, especially for complex, high-value assets such as commercial vessels. In the marine shipping industry, maintenance is not only vital for technical reliability, but also a requirement enforced by international regulations and classification societies. Improper or inadequate maintenance planning may lead to unplanned downtime, resulting in loss of availability and potential revenue, increased life cycle costs due to premature failures and emergency repairs, safety hazards, which can escalate to environmental and human risk, regulatory non-compliance, subjecting the vessel to detentions or fines. Factors influencing ship maintenance strategies. Several technical and operational factors shape the development of an effective maintenance plan. 1. Ship design and construction materials. Maintenance considerations start at the ship design phase. For instance, using high-tensile steel allows for lighter ship structures, but comes with the drawback of faster corrosion, necessitating frequent inspections and surface treatment. Similarly, applying epoxy coatings in ballast and cargo tanks mitigates corrosion risk and extends intervals between maintenance cycles. 2. Environmental conditions. Saltwater exposure, humidity, biological fouling, and variable temperatures heavily influence maintenance intervals. Ships operating in tropical waters typically suffer faster biofouling and corrosion compared to those in colder environments. 3. Component criticality. Critical systems, e.g., propulsion, electrical generation, ballast control, cargo handling, are prioritized in maintenance scheduling. Any fault in these components can compromise the entire vessel's operational readiness. Classification society and regulatory compliance. Classification societies such as DNV, Det Norske Veritas, ABS, American Bureau of Shipping, or Lloyd's Register set mandatory inspection and maintenance standards. Ships undergo annual surveys, intermediate surveys every 2.5 years, special surveys every 5 years. These surveys include inspections of hull integrity, propulsion systems, safety equipment, and compliance with IMO and SOLAS regulations. Ship maintenance locations and scheduling modalities. Ship maintenance can occur in several different operational settings. Dry docking involves taking the ship out of water for underwater hull inspection, painting, and major overhauls. At anchorage or port, intermediate level maintenance such as valve replacements, engine diagnostics, or HVAC servicing. At sea, minor adjustments and monitoring tasks via onboard engineers. Depending on ship type and operation, different shipyards or floating docks may be utilized, especially for vessels like LNG carriers, cruise ships, or large bulk carriers. Types of maintenance approaches. The marine industry adopts several maintenance methodologies, each suited to different operational needs. 1. Preventive, planned maintenance system. Scheduled by running hours, e.g. every 4,000, 8,000 hours, or calendar dates, e.g. semi-annually. Ensures machinery is maintained regardless of its current condition. Reduces risk of failure but may lead to premature part replacement. Corrective breakdown maintenance performed after machinery fails. Maximizes part utilization but introduces the risk of secondary damage and emergency costs. Incompatible with critical systems where redundancy isn't possible. 3. Condition-based maintenance, CBM, uses sensors, diagnostics, and real-time data, vibration, oil analysis, thermography to predict failures. requires skilled interpretation and data infrastructure, supports optimal resource utilization, and avoids unnecessary interventions. 4. Reliability-centered maintenance, RCM, a holistic strategy that integrates risk assessment and failure mode analysis, FMEA, applied selectively to maximize safety and cost efficiency. Typical shipboard maintenance tasks. Maintenance activities on ships can be grouped into the following key operations. Inspection, routine visual or diagnostic checks to assess wear or anomalies. Minor overhaul, disassembly and cleaning of subsystems like pumps, compressors, or filters. Major overhaul, complete disassembly, inspection, and part replacement, e.g. main engine crankshaft inspection. Survey, performed by Classification Society surveyors, often aligned with major overhaul schedules. Technological advancements in marine maintenance. With the integration of Industry 4.0 technologies, modern ships are increasingly adopting advanced solutions such as IoT and smart sensors for real-time monitoring, digital twins of engines or entire systems to simulate wear and optimize schedules, automated maintenance management systems, CMMS, for tracking, scheduling, and compliance logging. Economic and logistical considerations. On average, 75% of shipyard activity during scheduled visits is dedicated to routine maintenance, with the rest allocated to damage repairs or vessel retrofitting. Maintenance-related decisions directly influence total cost of ownership, downtime and scheduling flexibility, fleet management efficiency. Conclusion. Marine vessel maintenance is a sophisticated discipline requiring careful planning, technical insight, and regulatory alignment. Effective maintenance enhances safety, ensures compliance, and optimizes operational efficiency, ultimately contributing to the sustainability and profitability of maritime operations. From dry docks to data-driven condition monitoring, the evolution of ship maintenance continues to shape the future of the maritime industry. Would you like a shorter summary version of this for narration or video scripts? I can also add diagrams or visuals if needed.